Good morning, good afternoon, and good evening, everyone. My name is Joe. I'm a material researcher at the Moldex3D. So today I would like to give you a brief introduction to a Moldex3D material characterization service. And due to the time limitations, since we only have 30 minutes, so I'll try to keep it as concise as possible without getting into too much of the details. So the idea is to give everyone here some flavor of what we do in Moldex3D material characterization labs and what kind of service we can offer to our customers and what you can expect in terms of the results. So when we are talking about material characterizations, it is important to go back to the basic and the fundamentals. So all we want to do is to gather as much material information as possible before we run the simulations. So the idea is that when we have all these material data, such as the viscosity, heat capacity, thermal conductivity, and so on, this will make your simulations much more accurate since your simulations involved runs based on the governing equations. And these governing equations will require material properties in order to solve for the free falls. So for example, when we look at the mass balance here, this will require your density of the material. And when we look at the momentum balance, there is also the viscosity terms and the energy balance. This will involve the heat capacity and also the thermal conductivities. And so in essence, when we are trying to solve these material functions or the governing equations, material properties is very important. Without accurate material properties, what we are doing is essentially solving these governing equations blind. So that's not something that we want to do. Okay, so we always highlight to our customers accurate material information provides better simulation results. So in a layman's term, this actually means that the garbage in equals to garbage out. So it's very simple. If you don't fit good and accurate data into your simulation tools, obviously you cannot expect good simulation results. So this is all we try to stress to our customers. Accurate material information is very important for better and accurate simulation results. So in my talk today, I would like to divide it into two parts. The first part is thermoplastics. What kind of material data is required to run the simulations for thermoplastics? And the other part is thermoset. What kind of material data is also required for thermoset materials? So basically, I'll divide it into two different parts: thermoplastics and thermoset. So our capabilities in the thermoplastic material characterization service will cover basically all the material properties that's listed here. So that's the viscosity. So by viscosity, I mean shear viscosities. So there is another material properties that's quite often heard. That's the extensional or elongational viscosities, but that's not what we are covering here today. And the other one is PVT. So it's a pressure, a specific volume, and temperature relationship. So it's very important in the packing phase. And thermal conductivity and heat capacities are both very important thermal properties. Without this, we cannot calculate how much heat is required to heat up the samples, or how much energy is needed to be removed from the samples when we try to cool the sample down from the melt state. And also mechanical properties is another important properties, okay? Because when we try to calculate warpage predictions, mechanical properties, the Young's modules, or the Poisson ratios are very important material properties. And some advanced material characterizations, including crystallization kinetics and viscoelasticities. So just to name a few. Okay, now there are many other advanced material properties. I'm just giving a few here to be named as examples. So why is crystallization kinetics important? So imagine that if you have thermal semi-crystalline thermoplastics, the speed at which material crystallize will obviously influence the PVT graphs. So this is very important that we consider the crystallization behaviors of the materials. And another very important term is the viscoelasticities. And so this is important is because polymer itself or plastic in general, in a broader sense, is not just solid materials. Actually, when it's going through the molding behaviors, its behavior changes from viscous to rubber-like, all the way down to the glacier regions. So these materials are what we call viscoelastic materials. So this is the laboratory equipment that we currently have in our lab. So we have a RG25 imported, which is responsible for measuring the shear viscosity, thermal conductivity, and also if you have high pressure materials, high pressure materials such as a PC or PMMA, then we can work with the counter chamber to simulate what is going on in the actual molding conditions. Okay, and we also have another PVT instruments here. So the PVT instruments allows us to measure specific volume at different temperature and pressure. So this is very important for warpage predictions because our volumetric shrinkage relies on PVT curves. And MCR is another important tool. So this allows us to measure shear viscosities at the low shear rates. So during injection molding, people often think that it's a high speed process. That's true in most of the cases. But when we are transitioning from injection phase to the packing phase, and the shear rate might be low. So we also need to capture the shear rate data in the low shear rate regions. Okay. And the DSC data will allow us to capture the important glass transition behaviors of the materials, such as glass transition temperatures or the crystallization temperatures. And the TMA will allow us to capture the thermal expansion coefficients. Okay, so these are all very important tools. And the Instron mechanical testing device will allow us to capture the mechanical properties, the Poisson ratio, and the Young's modules. Okay. So the viscosity measurements actually during the injection molding process, you can see from the top left-hand corners in the actual injection molding process, the shear rate is rather high, from tens of thousands to hundreds of thousands. But the closest commercial machines that can measure the shear rates in that range is the capillary diameters, so which is depicted on my lower right-hand side. So this is the capillary diameters. And the other instrument is called a rotational diameters. And the rotational diameters will capture the shear rate range from the lower, maybe 10 reciprocal seconds, all the way up to 100 reciprocal seconds. So together, both of these will cover the shear viscosity curve from the Newtonian regions all the way to the non-Newtonian regions, which is depicted on the lower left-hand corners. So these two instruments work on different principles. So, for example, the capillary diameters is based on a pressure-driven flow. So you have the samples that's sitting inside of the chambers, and the pistons will move through at a relatively high speeds. to push out the samples through a very tiny capillaries in order to generate very high shear rate. And on the other hand, the rotational rheometers is based on a drag flow. Okay, so this is in contrast to the pressure-driven flow of the capillary rheometers. So these two instruments will basically give us shear rate, shear viscosities in the different shear rate regions. Okay, so for the shear viscosities, just talking about the general injection molding process from mid to high shear rate regions. So we have RG25 and also another instrument, Scotec, based on manufactured here in Taiwan. So these two instruments will allow us to measure shear rate range from a mid to high range. So we can cover basically from 100 reciprocal seconds all the way to 10,000 reciprocal seconds. And the maximum temperature range is about 400 degrees Celsius. So it's sufficient for most of the engineering plastics, and also for it's even sufficient for some of the tough engineering plastics such as PIC, and also such as some nylons. So this temperature range is sufficient. And once we gather the data, we will fit it using the appropriate models. So one of the models that we commonly use is called cross WLF models. So you see on the left, lower left-hand pictures, the dotted points are the data, and the lines are the fitted data using the models. So you see that the predictions and the data agrees quite well. So after we have the predictions from the data, then we have the material parameters for these models. Then we can use these material parameters to predict the shear behaviors under any different temperatures and also different shear rates. So this is the essence of using material models to do the predictions. Okay. And just like I said, the low shear rate data will be covered using different instruments. This is a parallel plate rheometers, MCR 502. And we can measure it using different modes, constant rotations or dynamic oscillations, depending on the needs. So, and the frequencies for dynamic oscillations can go from 1 to 628 radians per second. And we can similarly, once we have the data, we can also fit it using appropriate models. So one of the models that we use here is called cross WLF models. So you can see on the lower left-hand corners, the shear rate range is from 0.01 to 10 reciprocal seconds. So this is actually from the low to a mid range of the shear rate. Okay. And one of the important parameters is the temperatures. So you see on the left-hand corners, we have graphs that on the y-axis is there is a TB parameters, and on the x-axis is the temperatures. So you can think about it this way: the TB is the temperature sensitivity of the materials as a function of temperatures. So the steeper the slope, the more sensitive the material is in responding to the temperatures. So when we are talking about these temperature sensitivities, mostly for PMMA and PC, you see that these materials are very sensitive to temperatures. So that's why when we are talking about for optical moldings, optical component moldings, temperature is very important, such as PC and PMMA. However, when we are talking about molding for PE or PP, these kind of materials, you see that the slope is not as steep. So rarely, if we have any deviations in the temperatures, this will change your viscosities that drastically. Okay, so the graphs on the left-hand side tells us a lot about the temperature sensitivities. And on the right-hand side, this is runner leading up to the nozzles. So you see that in the centers and also in the areas closest to the wall of the runners, the viscosities, temperatures are actually quite different. And in the centers, the temperature is actually colder, and near the wall, the temperature is actually hotter. And this is due to a shear heating. And these materials will fall at a high shear rate. And since plastic itself is not a very good thermal conductors, the heat will accumulate it and actually becomes accumulated at these regions, and the temperature will become higher and higher, and the viscosities will become lower. So that means that if we don't capture the viscosity profiles accurately, that means that we cannot run the simulations accurately for these kind of predictions. And this is a product that's a lens product consider and without consider the temperature imbalance. So when we don't consider the temperature imbalance, you see the melt front is quite flat. And so this is not representing the actual case. The actual case is on the top corner, is on the top figures. So you see that the melt front on the right-hand edge and left-hand edge actually fall some faster. So this is the case when we actually consider the temperature imbalance, or the melt front on the edge will fall faster. So when we consider the temperature imbalance, we can capture this kind of behaviors. And for the high-speed injection process, it used to be that a long time ago, we used to make our cell phone back cover case with the injection molding process. And for this kind of injection molding process, the injection speed is quite high, and that comes with a high injection pressure as well. So this is what we call thin wall applications. So for plastic itself, when it's at the relatively low pressure, there is significant free volumes in the systems. However, during the injection molding process, high-speed injection molding process, the pressure is high, so that squeezes out the free volumes in the systems. And this kind of phenomena cannot be captured in the previous simple testing methods. So that's why we propose this. In the past, that we only consider viscosities as a function of shear rate and temperatures. But now we propose that we consider the viscosities as a function of shear rate, temperature, and pressures. So this is very important when we want to consider when we want to do the viscosity predictions correctly. Okay, so here we have a counter chamber. So I'm not going into too much of the details since we are we have a limited amount of time. So the counter chambers will simulate what is going on in a pressurized environment. So in this kind of pressurized environments, we have different pressure sensors to measure the pressure drop. Then we can move the pin for different settings to generate different kinds of pressure settings. So this will allow us to generate different kinds of counter pressure in the systems, and from that we can correlate to the increase in the viscosities with the different counter pressures in the systems. So you see from this graph, higher pressures will generate higher pressure drop in the systems, and lower pressure will generate lower pressure drops in the systems. So this is just a graph that's representing viscosities as a function of pressures. So this already tells us a lot about the importance of pressures in the injection molding systems. Okay, and again, here is just a viscosity curve at different temperatures and also different pressures. So for example, if we are just looking at the viscosity curve at 285 degrees, high and low pressures, already we are seeing that for the high pressure case, the viscosity curve is always higher than the low pressure case, and this is due to the decrease or due due to the decrease of the specific volumes, free volumes in their systems. So the pressure, those polymer chains are more close to each other, and there is more frictional force in that case. Okay, and here I just want to highlight that in the previous results, so when we don't consider the pressure effect and also contrasting when we are considering the pressure effect in our current results. So you see, for the pressure predictions, there is quite a significant gap when we don't consider the pressure effect. In the current result, when we are considering the pressure effect, the experiments and the simulation predictions are quite close to each other. And in the dimensional predictions, when we don't consider the pressure effect, you see that no matter it is from the length perspective or from the width perspective, there is some gap. And especially from the length perspective, there is a significant deviation from the experiments, and also between the experiments and the analysis. Okay. However, when we consider the pressure effects in our predictions, the dimension in the length-wise, in the length dimensions, and also in the width dimensions are quite close to each others. And PVT is another very important tool in our predictions. So I'm not going to too much of the details, but here is a specific PVT diagrams that covers different pressure settings and different temperature settings. So what we can do is that we will take the samples and do it at the different pressure and temperature settings, and our measuring process is by a cooling process. And because during injection moldings, once you inject your samples to the mold, this is a cooling process. Everything cools down from that points on. So our predictions, our experimental methods is based on cooling isobaric cooling process. Okay, and this is PVT diagrams that predicts what happens during the injection molding process. So you see that the red curve is the PVT curve. That's closer. That's near the gate, and the blue curve is the PVT curves that's further from the gate. So already the first thing that comes to our attention is that there is a significant deviations between these two areas. So always, what we are trying to do is that we're trying to optimize our PVT curves, try to make it in as uniform in each area as possible. So this will require us to have the PVT data to optimize our packing profiles. So without the correct PVT data, it is very difficult to run the optimal PVT optimizations. Okay, so for accurate warpage predictions, so if your materials is semi-crystalline materials, we would suggest that you should also considering the cooling effect, because the PVT curves will also be influenced by the cooling effect. So from here, the red curves here is a PVT curve for a very slow cooling process, and the blue curve and the green curve and the blue curve are the PVT curves for different cooling rates. So you see that with the faster cooling rates, the PVT curves gradually becomes aligned. Okay, that means that there is not sufficient time for the materials to crystallize. So it is quite important for these materials to have their crystallization kinetics measured properly. And for the optimized packing profiles, these are based on optimized PVT curves. So so for example, on the bottom figures, the optimized PVT curves will give much better warpage predictions. Whereas on the top figures, if we don't optimize the warpage, the warpage is quite high. Okay, so because the PVT curve is not optimized in this case. So this highlights the importance of having the accurate PVT curves, so that when we are trying to run simulations, we can use this as a baseline to do the optimal packing. Okay. And thermal conductivity is also very important, but since I'm running out of time, I will just skip it. Okay, so we will measure different. We will measure thermal conductivities for different temperatures, because it is also a function of temperature. So we will do that for the materials. And CP is another important parameters. So the CP here is based. We follow ASTM standards, so we will heat the material up to a molten state and then cool it down at a constant cooling rate, and then is CP heat capacities. Okay, and this the DSC will tell us a lot about the physical properties of the polymers, such as the melting temperature, the crystallization temperatures. And for the amorphous, it will tell us the gas transition temperatures. So these are all very important for our simulations predictions. Okay. And TMA is another one. So this will measure the the thermal expansion coefficients. So this will allow us to take into account of the thermal expansions in flow and cross-flow directions. Because if you have a fiber fill materials, these materials will have different thermal expansions in the two different directions. Okay, and mechanical properties is another very important parameters. So because we need the tensile modules, and we also need the Poisson ratios for our warpage predictions. And crystallization kinetics. Okay, so this is the effect of the crystallization kinetics. So basically, we will use this high cooling, high speed cooling process. So the maximum cooling rates can go up to upwards of 600 degrees per minute when we use liquid nitrogen. So, and once we have the data, we can use appropriate models. So the model here is called Nakamura's models to take into account of the cooling rate effect, and also its percentage of crystallization during the process. Okay. So here is a comparison of the predictions, the shrinkage dimensions with and without considering the crystallization kinetics. So the dotted line is the CAD dimensions. So we can call this the 0th dimensions, or the baselines. And when we don't consider the crystallization kinetics, okay, everything is very close to the CAD dimensions, but that's the blue lines. But these are very far away from the experiments. So the experiments is the green lines. However, when we consider the crystallization kinetics, so that's the red light. So the predictions is much closer to the experiments. So this highlights the importance of the crystallization kinetics in our systems. Okay. Okay. So to summarize, accurate material data are essential for successful simulations and the injection molding process. And our material testing service can provide a complete material characterization service for simulation requirements run in Moldex3D simulations.